Hello, everyone. This is Nuclear Chemistry Unit Review with Ms. Rodriguez, and today we're going over all of the topics that are covered in the Nuclear Chemistry Unit in high school chemistry. So starting off with some definitions, our first definition is atoms that emit radiation spontaneously, and that is called something that is radioactive. An unstable atom undergoes this to become stable. It undergoes radioactive decay. These are released by radioactive materials. We call that radiation. It's determined by the ratio of neutrons to protons. That's what we call stability, so nuclear stability. And a reaction that changes the atom's nucleus is called a nuclear reaction. Now, let's go ahead and compare and contrast the difference between fusion and fission. So fusion reactions combine atoms, while fission reactions split atoms. Nuclear fusion occurs in stars, so like the sun, and nuclear fission has only ever been found in one place in nature, and that was in the ground. Nuclear fusion takes a lot of energy, while nuclear fission takes little energy. Nuclear fission was used to make the atom bomb, while nuclear fusion, it's never been used in warfare, but it's called the hydrogen bomb. Nuclear fission reactions are used in nuclear power plants, while the energy usage for nuclear fusion reactions, even though it would make a lot of energy, even more than fission reactions, the use for it is still experimental. Nuclear fusion reactions use hydrogen as fuel, and fission reactions can use different atoms, but most commonly it uses uranium as fuel. Now let's look at these three isotopes for carbon, and let's determine how many protons, neutrons, and electrons are in each of the isotopes. Since all three of these are carbon, and they all have an atomic number of 6, that means protons for all three of them would be 6 protons. And since we don't see a charge, we're going to assume that it's neutral. That means that there's also going to be 6 electrons. The differences between these carbons is their mass number, which means that they are isotopes, so they have different numbers of neutrons. To get the mass number, it's proton plus neutron. We already know it has 6 protons, so that means this carbon has 5 neutrons. This carbon has 6 neutrons, and this carbon would have 8 neutrons. Let's go ahead and graph where these carbons would be on our stability graph. So the first carbon has 6 protons and 5 neutrons. So 6 protons, 5 neutrons would be somewhere around here, and that's going to be our first carbon. So let's go ahead and label that 1 just so we know. Our next carbon has 6 protons, 6 neutrons, so 6 protons, 6 neutrons would be somewhere around here. Let's go ahead and label that 2. And our last carbon has 6 protons and 8 neutrons, so that'd be all the way up here. So let's go ahead and label that 3. And the question is asking, based on their position in comparison to the line of stability, circle the isotope that's most likely to undergo radioactive decay. The further an isotope is from that line of stability, the more likely it is that it will undergo radioactive decay. So out of the 3 carbons presented, the most likely to undergo radioactive decay would be C14. Now let's talk about half-lives. The half-life of cobalt-60 is 5 years. If the initial sample contains 10 grams of cobalt-60, complete the chart below to show the grams at each of the half-lives shown in the graph. So we're starting at 0 years. One half-life is every 5 years. So one would be 5 years. Two half-lives would be 10 years. Three half-lives would be 15. And four would be 20 years. And every time we go through a half-life, there should be 50% less. So half of 100 would be 50%. Half of 50 would be 25%. Half of 25 would be 12.5%. And half of 12.5% would be 6.25%. And using that same logic, we're going to do the same thing to the grams. So at 0 half-lives, there were 10 grams. After the first half-life, so after 5 years, there should be 5 grams left. After another half-life, so again, half of the previous amount, there should be 2.5 grams left. After another half-life, you end up with 1.25 grams left. And after 4 half-lives, you end up with 0.625 grams. And that's how many grams of the cobalt-60 is left after 4 half-lives. All right, now let's go over alpha, beta, and gamma particles. So what do these even look like? An alpha particle is an He with a mass number of 4 and an atomic number of 2. A beta particle can either look like this or like this, but in both cases, it has a mass number of 0 and an atomic number of -1 because it's an electron. So it has 0 protons, but it contains 1 electron. And a gamma particle looks like this, and it has a mass number of 0 and an atomic number of 0. And if we rank them based on their penetrative strength with the least penetrative first, that would be alpha particles can penetrate the least amount of things. Alpha particles are actually so weak that they can't even go through paper. Beta particles would be the second most penetrative, so they can go through paper, but they're stopped by aluminum or glass. And gamma particles are the most penetrative. They go through most things. The only thing that could really prevent a gamma particle from penetrating is a thick layer of concrete or steel. And let's look at what an alpha, beta, and gamma decay look like for the same atom. So looking at technetium 95, what would it look like after it goes through an alpha, beta, and gamma decay? So we're going to start off with the same thing. Technetium on the periodic table is Tc, and it is number 43 on the periodic table. And we already know it has a mass number of 95 because the problem told us. So we're going to start off the same way each time. And we're going to see what happens to this technetium after it undergoes the different types of decay. So the first decay is an alpha decay. So we have our alpha particle. And remember, we treat this arrow like an equal sign. So whatever we have on the left, we also got to see on the right. So the law of conservation of mass is still in effect. So we have 95 over here, we have 4 right here. So what number plus 4 gets us to 95? 91. And what number plus 2 gets us to 43? 41. And looking at the periodic table, number 41 would be NB. So after going through an alpha decay, 9543 Tc becomes 9141 Nb. Next, we have a beta decay. So beta decay means it releases a beta particle. And again, everything has to stay balanced. So what number plus 0 gets us 95? What number minus 1 gets us 43? And if we look at the periodic table, the element with an atomic number of 44 is Ru. And that's what happens to technetium when it goes through a beta decay. And for our last one, which is our gamma decay, these are actually the easiest to do because if you notice, gamma decays do not affect the mass number or the atomic number. So it's still 95 and 43. And because the mass number and atomic number didn't change, neither does the element. So technetium is still technetium. It just released a gamma ray. Now let's do a decay series. So decay series means whatever product you end up with the first decay, that's going to be your starting point for the next decay. So starting at the top, and we're looking at the decay series for platinum 120. So we're going to start with platinum 120, and platinum is atomic number 78 on the periodic table. The first decay that it undergoes is a beta decay. That means it releases a beta particle. And 0 plus 120 gives us 120. And 79 minus 1 gives us 78. And atomic number 79 on the periodic table would be Au. And since this is a decay series, the Au that we ended up with after the beta decay is our starting point for the next decay. So it's going to be our starting point for the alpha decay. So 120, 79, Au, and it's going to go through an alpha decay. So it's going to release an alpha particle, so that's 42He. And now let's figure out what the product is. So what number plus 4 gives us 120? That would be 116. What number plus 2 gives us 79? Would be 77. And atomic number 77 on the periodic table would be Ir. And again, we take the product from the previous decay, and it's our starting point on the next decay. So 116, 77 Ir is going to go through a second alpha decay. So again, an alpha particle is released, and now we figure out our new product. So what number plus 4 gives us 116, 112, and what number plus 2 gives us 77, 75, and atomic number 75 on the periodic table would be Re. And again, we're going to take our product from the previous decay, and it's going to be our starting point for the next decay. So 112, 75 Re. And here's our easiest type of decay, which is a gamma decay. It releases a gamma particle, but other than that, nothing changes about the atom. So it's still 112, 75 Re. And our last decay, and let's go ahead and take our product from the previous decay. So 112, 75 Re. And it goes through one more beta decay. So again, releases a beta particle. 0 plus 112 is still 112. And we have what number minus 1 gives us 75. That would be 76. And so our final product from this decay series is 11276 OS. All right, that is everything you need to know about the nuclear chemistry unit in high school chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If you found this video helpful, make sure you hit that like button and subscribe so you don't miss any of my future chemistry content. If you would like access to this exact study guide, it is on my TPT store called Chemistry Made Simple, as well as additional worksheets, labs, and activities that align with this unit and all other units of high school chemistry. I hope you have a great day. Bye.